So let's go on to the next module, which is attention mechanism. So let us motivate, not the task of attention, let us motivate attention mechanisms with the help of machine translation. Okay. So what is happening in the models that we have seen so far? The current model that we saw for machine translation. By the way, all the models that I have shown you so far are wrong or rather incomplete. We'll complete all of them, right? And that's where attention fits in, okay? That was for the camera. The encoder reads the sentence and it computes the encoding once, right? We read the entire sentence and we encoded it. And then we had these two options, either pass the encoding at the 0 time step or pass this encoding at every time step. Is this how humans translate a sentence? What's the human analogy for this? You have read the sentence once, done, and now you're going to remember this entire thing throughout and then translate. Imagine if you're doing this for sentences which have 25 words, which is a typical Wikipedia sentence. What's wrong with this? You have read the input once and you have encoded it. What's likely to happen? You will forget some things, you're going to lose information. Not just that, is the entire sentence important at every time step? Only certain words are important. So you see there's conceptually something wrong that we're doing here. We're just saying, okay, I'll encode the sentence and then start decoding from there. Okay, that's the conceptual error that we are making. So let's see how humans actually translate, right? So when producing one word in the output, suppose my input is the Hindi sentence and I have the output sentence. When I'm trying to produce the first word, I actually compute this probability distribution which tells me which of the input words that I need to focus on. At this point, it's okay if I don't know what's the translation for ghar or ja or raha or hu. As long as I know the translation for main, I'm done, because that's the word which I first need to produce there, right? So I'm going to say that at this point, I only need to pay attention to the first word in the input and I can ignore everything else. What about the second time step? I just need to focus on the last word. What about the third time step? Is it always going to be that I only need to focus on one word at a time? No. What about the third time step? I'm sorry, I'm assuming everyone understands Hindi, but I think this is a small sentence, I can assume that. What will you focus on? Ja and rahi, right? So you want to focus on both these things and not on anything else. And what about the next one? Ho, right? So just on ghar and not on anything else. Is this what the model, encoder-decoder model is doing? What is it doing actually? At every time step, it's focusing on the entire sentence because that's the encoding that you're feeding to every time step. That's the problem that we need to correct. We need to learn to pay attention to certain important parts of the sentence. Is the setup clear to all of you? Is the motivation fine? Not your motivation layers, is the motivation for this fine or not? Okay. The distribution actually tells us how much attention to pay to each input word at each time step. And ideally at each time step, we should pay attention to only certain words in the input. Okay. So let us revisit the decoder that we have seen so far. This is what the decoder looks like. In fact, I also have the encoder there. Now suppose, so currently what we are doing is we are either feeding S0 at the, we are either feeding the input embedding or the encoder embedding at time step 0 or at every time step. Now suppose there was an oracle which told us exactly which are the words important at time step t. Right? So in our example at time step 3, suppose it told us that the word going is important. Actually, we need to flip the input and output here also, right? But you can still understand, right? So I'm saying at time step 3, certain words are important. And suppose an oracle actually told us that these are the words which are important. What would you do? Assume that you have already run the encoder. What will you do now? And say someone told you that only this word is important. But why weighted? I'm just saying binary weights, right? Only this word is important. What would you do ideally? Just feed this blue vector to the decoder and don't feed everything else. Does that make sense? Suppose I told you that 2 words were important. Send those 2 words, but how? Concatenate. But now at certain time steps 4 words will be important. And you can't concatenate 4 words, right? Because then the dimensions will change. So what do? A weighted sum of the important inputs. Does that make sense? At time step 3 we saw that ja was 0.5 important and rahi was 0.5 important. So just take a weighted combination of those 2 blue vectors and feed that to the decoder. So you are not changing the dimensions at each time step because the blue vectors have the same dimension and just taking a weighted combination of those are going to give you the same dimension. Does that make sense? Okay. So in effect, what I'm saying is that I could just take a weighted combination of all the blue vectors that I have at the encoder, and the weights of this weighted combination right now, I am assuming that some oracle has given me. Is that okay? If I had these weights, does this make more sense than having the vanilla encoder-decoder model? Everyone agrees with that? Okay. Now the question, of course, is who is going to give us these weights? We'll come back to that later, but at least given the weights, this makes sense. So at every time step, we're just going to focus on the words which are actually important. Just take a weighted combination of those words, and we'll just feed that to the decoder. And intuitively, this should work better, because unlike before, where we were overloading the decoder with the entire sentence, remember 25 words, 30 words, entire sentence was being passed to the decoder. Now we are just overloading it with the amount of information that it actually needs to produce that particular word. Hence, intuitively, this should work better, right? Okay. Now, how do we convert this intuition into a model? In practice, of course, there is no angel who is going to come and give us these weights. There's no oracle. The machine will have to learn this from the data. Whenever you need to learn something, you need to introduce parameters. So I am going to now introduce a parametric form from the figure, which thing? For those of you who can't see, these are alpha 1, alpha 2, and so on. So now from the figure, we are going to introduce a parametric form for the alphas. Okay. Okay. So I'm going to introduce. I will come to alpha, and what do you think this weight should depend on? What I'm trying to say is that at the tth time step of the decoder, so this is EJT, at the tth time step of the decoder, I want to find out how important is the jth word in the input. That's exactly what I'm interested in. At every time step of the decoder, of all the input words, I want to see which of them is the most important, right? So this is the quantity that I'm interested in, is how important is the jth input word at the tth time step. This should depend on what? What should it be a function of? For one, it should depend on what that word is, right? The other, it should depend on what has happened in the decoder so far. What has the decoder produced? So what is the input and what is the decoder stated so far, right? So if the decoder has already decoded the word ghar or home, it does not need to look back at home, right? That's why I need to know what's the state of the decoder. What captures the state of the decoder at time step t? ST. And what is the state of all the words that we have? It's captured by what? The HJs, right? This is H1, H2, H3, H4. Does that make sense? How many of you are fine at this point? Please raise your hands high above. Okay. How many of you have questions? Please ask specific questions if you have a question. All I'm saying is a couple of things. One is, at every time step, instead of the oracle giving me these weights, I want to learn these weights. Whenever I want to learn something, I have to introduce a parametric form, and then I learn those parameters. Okay. Now, what is the quantity that I'm interested in? I'm interested in this for all the input words. For the jth input word, I'm interested in knowing how important it is for the tth time step. There are several ways I could write this function. I'm saying that the two things that are important is, one, what is this jth word, which is captured by Hj, right? And what is the state of the decoder up to this time step, which is captured by St minus 1. You could think of various other equations. At this point, I am fine if you buy the intuition that this quantity should indeed depend on these two terms. It should depend on what has happened in the decoder so far and what does my current word actually look like. How many of you are fine with that? Please raise your hands up and high. Okay. Now, also the other thing that I would want is that across all the input words, this should actually sum to 1, right? I just want a weighted combination. I don't want arbitrary weights. It's just like taking a probability distribution over which word is important by how much. So if I have this EJT, how will I convert it to a probability distribution? Softmax, right? So I'll just compute the alpha j's as the softmax of EJs. Is that fine? Everyone gets this? Okay. Now we have still not seen what the exact form of attention is, of the f attention function is. So this is what the equation for the alpha j t's that we had, And alpha j d actually denotes the probability of focusing on the jth word at the tth time step. Okay? Now we are now trying to learn these alphas instead of an oracle telling us what these alphas are. So learning is always going to involve some parameters. So let's define a parametric form for alphas. And just a couple of notations. So from now on, hey, we didn't change this. We are going to refer to the decoder state as ST and the encoder state as SHJ. Okay, so these blue vectors are S's and these blue vectors are H's. Okay. Given these new notations, one among many possible choices for F attention is the following. I wanted it to depend on the current decoder state. I am making it dependent on the current decoder state, but I am also adding a parameter in front of it, right? I also wanted to make it dependent on Hj. I am making it dependent on that. I am also adding a parameter here. Why do I need this parameter? What's the dimension of this? Let's assume this is also, what's the dimension of this? Remember, after multiplying with U attention and after multiplying with W attention, the two vectors should be addable. Is that fine? Something cross D. What about this? Same thing cross D. Okay, good. Okay, so let's call that same thing as D1. What's this output then? The tan H output is vector scalar matrix, vector of size. You said matrix or scalar. Okay. it's okay. R square R raised to D1. What's the quantity on the left hand side? Vector scalar matrix, vector. Even though it has two indices, it's a vector. What is this quantity capturing? At time step t, what is the importance of the jth input? That's a, I'll keep asking till everyone replies, that's a scalar. Okay. Now you have scalar is equal to something multiplied by R raised to D1. So why do you need this something? So what's the dimension of that going to be? R raised to D1. So that's the dot product. So you see why we have these parameters. Okay. So what we have done is made it dependent on ST1 and Hj and also made sure that the output is a scalar. That's what these three parameters are doing. Okay. And these parameters will be learned along with all the other parameters of the encoder and the decoder. So now this is all fine. If it actually someone had given me the true alpha j's and I had predicted these alpha j's through that fancy equation which I just showed you, and then I added a dash function, softmax. That's the safest choice in this course. I want to learn something, so what should I add? Loss function. What would the loss function be? Say squared error loss. And then I want to adjust the parameters to minimize this squared error loss. Then all of this makes a lot of sense, right? Because then you can imagine that your U attention, W attention and V attention will get tuned in a way that the predicted weights are very close to the true weights. This we all understand. Given an objective function, we understand that the weights will get adjusted so that you adhere to the objective function. But the whole premise was that we don't have the true alphas. Because in the case of translation, no one is going to tell you that the kth word came from the jth word or the set of j words. Do you all agree with that? So if we had the true alphas, this makes a lot of sense because then we could have added a loss function which takes the loss of alpha true with respect to alpha prediction, and then in addition to our loss theta, which was the sum of the cross entropy errors, and then we could have jointly minimized this, and we could have hoped that the attention parameters would have been learned accordingly. In practice, we will not have this. In our translation example, we would want someone to manually annotate for every word in the output which is the set of input words from this which it came. This is not going to be possible. We cannot collect so much annotated data. So what do we do? Why should this model then work? It does not have any supervision. Why should this model work in the absence of such data? How many of you get the meaning of the question? How many of you see the problem? Please raise your hands. We are not given the true alphas and that's what our problem is. Then why should this work better? This works better because this is a better dash choice. Language model, better dash choice. What is the possibilities there? Better modeling choice. Why? Okay, I give you the answer. This works better because this is a better modeling choice. Why so? So I'll give you an analogy and the reinforcement learning fans will cringe, but they can just go out. So Suppose you're trying to learn a bicycle, how to ride a bicycle, okay? That's why I said they'll cringe. I already see some of you cringing. As if you guys have a copyright on bicycles, okay? So suppose you're trying to learn a bicycle, okay? And for some reason, you, in your infinite wisdom, you decide that you can learn how to ride it without holding the handle, okay? And you start trying to do it. It's conceivable that in a few years or decades, you will actually learn how to ride the bicycle, right? Even if you're not holding the handle, right? People do that, right? People can ride it without that. Now, the only thing that I do is, I come and tell you that instead of doing this, why not you try to hold the handle and then try to ride the bicycle, right? That is all I'm telling you. I am not giving you any other supervision. I've just given you a better model. I have said that instead of just trying to adjust the parameters with respect to your feet and the pedal and your back position, why not you also introduce this additional parameters where you're holding the bicycle with your hands and now try to figure out what kind of weights you need to put on your left hand, right hand, and so on. I'm not giving you any supervision for that. That you need to still discover on your own. Right? You will start riding it, you might fall on one side, you might fall on the other side, but you will eventually figure out what these weights need to be. Right? Because the second model where you hold the handle is a better model than the first model where you are not holding the handle. In the second model, you have additional parameters where you could adjust these parameters so that you could learn to drive better. That's a more natural way, more close to human way of learning how to ride a bicycle. The same thing is happening here. The second model, where you have a way of learning these attention on the weights. Even though I'm not, all I'm telling you is that, look, maybe if you decide at every time step which word to pay attention on, you might be able to do better than feeding the information from the entire sentence at every time step. That's all the information that I'm giving you, which is very similar to saying just hold the hand. That's not going to teach you how to ride a bicycle, right? You still have to do the extra work of learning these parameters. But now you're given a chance, you're giving the model a chance to learn these parameters. You're telling it that this is a better way of modeling it. With this, you should be able to learn better, right? So there is a hope of doing better because now the model is actually making a more informed choice, right? It's a more informed way of learning how to do translation by focusing on certain words at every time step. And now these parameters, how will they get adjusted? They will get adjusted because at a given time step, you produced a wrong output. You did that maybe because this parameter was wrong, which is the V parameter, or maybe because these recurrent connections were wrong, or maybe because your attention weights were not proper. So now adjust the attention weights, and that should, given sufficient data, it should be able to learn which words to focus on, just as humans learn how to do translation. Even when we are learning how to translate, or when we learn translating from one language to another, we are not given this word by word supervision. Right? We just do a lot of translations or read a lot of translations and somehow understand that while translating, I need to focus on certain words, and at every time step, this is the word that I need to focus on. So given enough words, it should be able to learn that. At least someone gets the joke, good. Yeah, so that's the hope. And in practice, indeed, these models work better as compared to vanilla encode. You don't know where the statement comes from. Fine. So now what we'll do is, so this entire thing hinged on hope only, right? That's all I'm saying. But it does make sense, right? Because you have these additional parameters which you can learn and you can backpropagate through them. And we'll just not stop there. We'll actually prove what happens, not prove, but demonstrate what happens in practice, right? So with this attention model in mind, let us look back at the encoder-decoder model that we had for machine translation, integrate the attention mechanism with it, and then let us see the end-to-end equations that we get, okay? So this is what the diagram looks like. The input and output still remains the same. You're just given the source sentence and the target sentence. In particular, you're not given which words to pay attention to every time step, right? That is not given. So remember that my input is not changing. It's still the same source sentence and the target sentence, okay? What's the encoder? Now try to work out the equations. I want you to write the equation for yt, which is going to be some composite function of x, where x is a vector. It's x1, x2, x3, all the words in the input, okay? And somewhere along the line, it is also going to have this attention equation. It's going to take a while, but at least try to imagine it. There are some hints in the diagram itself. You could take a look at it. I'm just asking you to convert the diagram to a set of equations. So encoder part is fine. I have computed the representation of each word at time step t. So this is a contextual representation of the word because it's aware of what the neighboring words are, right? Now what's the decoder going to be? What is the first thing at time step 1 or at time step t in the decoder? What is the first thing that I'm going to compute? The dash weights, the last time step of the decoder, of the encoder, sorry. What's the first thing that you need to compute at time step t? The attention weights. Speak up, please. What's the first thing that you need to compute at every time step? What kind of a combination I take of the inputs, or rather which are the words that I need to focus on from the input? Who tells us this? The attention weights. How will you compute the attention weights? Using this fancy equation that we had seen earlier, okay? Is this enough? I need to convert this to a probability distribution, right? That's just to ensure that everything is a neat combination. Once I know the attention weights, what do I need to feed the decoder? A dash combination of the inputs, a weighted combination. How do I take a weighted combination of the inputs? Summation I is equal to 1 to capital T alpha jt into hj, right? No, j. T is the decoder time step, j is the input word. So at the tth time step of the decoder, I am taking a weighted combination of all my inputs. The index of the inputs is going from j equal to 1 to t. By the way, did that answer your question? That's what you were asking, right? Okay. Is that fine? Okay. Now what next? Now I want to produce a word at the output. What's the decoder going to be? First thing that I'm going to do is, decoder is a dash, RNN. Okay. What's the input to the RNN at every time step? The previous predicted word as well as the weighted combination input that you have given it. Does that make sense? Okay. And then finally, how do I get the probability distribution? Is that fine? Actually, this should be a distribution, right? LT does not make sense. LT is argmax of this. Right? And what's the loss function? Cross entropy. There is no change in the loss function, right? Loss in the algorithm remains the same. So I've seen these set of equations. Now, how many of you are confident of going back and modifying all the wrong encoder-decoder models that we have covered in the initial part of the lecture, modifying them to add the attention equations in them? How many of you can do that? Please raise your hands. I'm not going to ask you, just do it so that I feel happy. You can do it, right? Any questions at this point? Very good, okay. Okay, so you can go back and try adding attention mechanisms to all the models that we have seen before, right? See how will you compute. So remember, the only purpose of, okay, what kind of a network is the attention network? It's a single feed-forward neural network, right? This is just transforming a simple linear transformation of the inputs and then a non-linearity on top of that, and then just again one more transformation, right? It's a simple feed-forward neural network. Only these three equations somehow need to be fitted in all the other models that we have seen so far, right? This is a very generic framework, just as the encoder-decoder framework was a very generic framework. The encode attend decode framework is also a very generic framework. You can go back and model all the applications that we saw, and you can change them to adhere to this, okay? And try to answer the same set of questions. What's the data? What's the encoder? What's the decoder? What's the loss? What's the training function? And in particular, remember that when you go back and revisit all the applications that you have done, the data is not going to change. No one is going to give us the supervision for the alphas. That's one thing which is not going to change, okay? Okay, so here's one more thing. So this is probably tied to his question, like how do we be sure that the alphas actually learn something meaningful? Now what do I mean by this? If I have to convince you that alphas are actually learning something meaningful, and let's take the context of machine translation. What do I need to show you? Suppose the model has generated an output for a given input sentence. It has generated a translation. What do I need to show you to convince that it's learned some kind of weights? At every time step, what should I show you? What do the attention weights look like, right? So let's see. This is a common trick, or not a trick actually, this is probably a trick only, but this is a common thing which is used in several papers, and that's why I call it a trick, because it's a trick to get your paper accepted, that you actually show what the attention weights actually look like, right? So on this is the input document, and this is the summary that you want to generate. Okay, and what you see here is that at different time steps, so look at the last time step, terrorism, it paid maximum attention to the word terrorism in the input, right? So you can draw this matrix. Suppose you had capital L time steps in the output and capital T time steps in the input. So you could draw this L cross T time step or T matrix, which tells you what was the attention paid to every input word at every output time step. Do you get that? Do you see what this matrix is? This heat map is essentially a matrix of size L cross T, and every cell here tells you how much attention you paid to a particular word at that time step. And the darker the cell, that means more the attention that you paid. Everyone gets this? Okay. So what this is saying is that probably, see, when you wanted to generate Russia, the maximum attention was paid to Russian and maybe some other words also. Sometimes it does not work very well, but sometimes it does, right? So for calls, the maximum attention was paid to called, and then similarly for front, the maximum attention was paid to front, and so on. So you see some meaningful patterns that it is learning here. And here's another example for machine translation. So roughly, to quickly understand what this figure is, right? So this is, I think, English to French. Is it French? Yeah, it's French, or French to English translation, which is largely monotonic, right? That means at the fourth English word, you would end up paying attention to the fourth French word, right? That means you're almost doing a word by word translation. And that's exactly what you see, that most of the attention is along the diagonal, right? So it's learning some meaningful attention weights. As always, helpful if you're using an attention mechanism to plot this and see if it's actually learning any meaningful attentions or attention weights or not, right? So that's a common trick which people use.